Okay, good. So, okay. From, oh, sorry. So, this view is okay? Or should I close the window on the right hand side? Participant window. No. Where is it? This one? No, it's not. Hmm? View standard. I see. This is on the top instead. But it's okay. Hmm. Can I? Okay. So, any questions from previous classes? You learn how to model VLE, right? And also you learn how to test the VLE data we obtain from experiment, okay? Through point-to-point test, area test, so many things, yeah. And then from the data we obtain, we plot between GE over T, right? GE over T, X, A, X, B, and then, well, we identify the parameters, okay? So if we model it using two parameter or one parameter, okay, we obtain different model, right? Like this one, where, okay, for one parameter, we obtain symmetrical model, right? Yeah, interesting. We have plenty of room here. So why don't we expand it? But I don't know how to do it. It's all right. And yeah, Magnus equation also need two parameter, right? Uh, one equation, we also need parameters, two parameters. And for Wilson and RTL, of course, more parameters are needed. Okay, we right. Mhm. And what happened? Annihilative, yes. Mhm. Also, would like to remind you again about activity coefficient at infinite dilution. Okay, so for infinite dilution, you also obtain parameters. Okay, log gamma A infinity. Okay, from infinite dilution parameters, you can identify the activity coefficient model also. We learn about already. Okay, and also we talk about the pressure and temperature liquid phase activity coefficient. Okay, the effect of pressure, right? How gamma change once pressure change, and also gamma change once temperature change, right? Okay, so it depends on the pressure. It depends on the volume change. Okay, volume change when you mix A and B, right? How the volume, I mean molar volume of A and B change, okay? If there is volume change, of course, you can expect for the change of pressure has effect on gamma is more sensitive to pressure, okay? And in case of, what's it? Type 1. Type 1. What is type 1? Hmm? What is type 1? What is type 1 solution? Ideal solution, okay? For ideal solution, of course, we no change in gamma, right? Because gamma always 1, okay? And for the effects of gamma, of temperature on gamma, gosh, depends on the heat of mixing, okay? The enthalpy change, okay? When you mix A and B, how the enthalpy of each molecule change, okay? If it's large, of course, it has more sensitive to the temperature change, okay? And for ideal solution, what happened to ideal solution? You don't have effect of temperature on gamma, okay? No matter temperature change, it doesn't change with gamma, right? We can also ประกรณ์เกียรตินะปิดไมค์ด้วยครับ We can identify, we can apply the activity coefficient model obtained from binary system to ternary system also. Okay, you can look for more detail in the textbook. Okay, and what else? For Weber phase non-ideality at low pressure, we assume that pressure, the Fugasti can be represented by pressure, right? However, the discrepancy between pressure and Fugasti becomes more larger in case of higher pressure, okay? Once pressure increase, the deviation or the discrepancy becomes larger. So how can we compensate that discrepancy, or how can we take that change into account? We, of course, you cannot use PYI anymore on the left hand side of the VLE equation. You need Fugasti, okay? And it must Fugasti of that component, okay? So how can we identify or calculate Fugasti of component I? You can calculate it from that Fugasti coefficient, okay? Because Fi over Pyi equal phi I hat, right? So phi, what is phi I hat? Phi I hat is Fugasti coefficient, okay? At low pressure, this thing becomes 1, right? Okay, so based on this idea, we can find phi I hat by integrate this term, okay? We need exponential of minus 1 over RT, and we integrate from P0 to P, okay, from 0 to P of Fi dp, okay? Or you can write This one, exponential of integrate from 0 to p of zi minus 1 over p dp. Okay. Okay. And you can use, what is it, your EOS, any EOS you have learned so far, to plug to this equation in order to find the Bugatti coefficient. Okay. Okay. You learned previously before midterm about, I believe that you learned a lot of EOS, right? And in the first class, right? First time I met you, I briefly introduced you about EOS, but I assume that you have learned it before, right? We don't spend much time on that. Okay, all these are Weber-Fest non-ideality. Okay. Yeah, this is VLE for EOS. For higher pressure, you should use EOS to estimate fire hat. Okay. The most widely known equation design for this purpose is Self-Reddish-Kwong and Peng-Robinson. Okay, to plug this in. Okay. And the other thing is solubility parameter. There's a connection between solubility parameter and gamma. If you don't have activity coefficient model, you don't know activity coefficient, but you have information regarding the delta. It's a solubility parameter. You can estimate the activity coefficient by using solubility parameter. Okay, that's okay. This is solubility of gas in liquid. Okay, so we move to the next chapter then. Oh, I should give you the textbook also. One moment. Is the slide. Oh, this one also interesting in RTL because you're going to use it. Okay, and in RTL also interesting. So I give you the okay. formation of the NaCl. Okay. And Wilson equation. Okay. So well later you can read by yourself, okay, about NaCl. We don't spend much time on that. The next thing is now we move to the new chapter. Okay. Chapter 10, right? No, which chapter is it? Chapter 10? Right? Chapter 10. Okay. Okay. So now we consider the case where the pressure increase. Okay. And approach very high pressure. Okay. We consider in case of very high pressure. And you see that once we increase the pressure, what happened to the K? This figure show you the relationship between pressure and K. Okay. K is y over x. Okay. Y over xi. Okay. We have information of methane, ethane, propane, pentane, hexane, heptane, and decane. What happened? Once the pressure increasing. Okay, at low pressure, we start from low pressure first. And then once the pressure increase, what happened to K? It's decreased first, right? And decrease linearly. Okay? And once the pressure is high enough and then increase again, all components approach to the same K. Right? Is approach to the same point. That one is K is 1. Okay? Someone. Okay? So what does it mean? When K equal 1. Pardon? Equilibrium. No, it's not that one. Equilibrium. We all have equilibrium. Every point is equilibrium. Not only that point, but that equilibrium, K equal 1. What does it mean? What is the definition of K? K is y over x, right? We expect the composition of y of Weber equal the composition of liquid. So what does it mean when once the compositions are the same for both phases? We cannot distinguish between Weber and liquid because both phases approach the same state, right? The same phase. Okay? Okay. And our composition, no, components, all components approach the same, approach to the same point, right? Where you cannot distinguish between Weber and liquid, okay? Because the composition is the same. Okay? Here, as the pressure approach 3000 psia, right? The Ki approach 1, indicating that the composition of the liquid and the vapor are approaching one another. Okay? Okay, so the composition in both phases are identical, right? Now we consider the critical phenomena of pure species first before we move to the mixture. For pure component, what do we have for is water, right? Okay, this one is water. Okay, pure component of water. Okay, so we have liquid on the left hand side. We have vapor on the right hand side. Okay, under this dome is a Weber liquid region. Okay, we have equilibrium between vapor and liquid. Okay, and on the left hand side is a saturated liquid. Okay, and subcooled liquid. Okay, on the right hand side we have saturated vapor and superheated vapor. Okay, so there's a critical point that connects between saturated liquid and also saturated vapor over there is we call it critical point, right? So actually, this is a pure phase, but in case of mixture, also the same. Okay, similar behavior. Okay, and Weber specific volume fall rapidly with increasing pressure, right? When the pressure increase, the uh, specific volume fall rapidly. Okay, and at a critical point, the liquid and vapor becomes the same. Okay, you cannot distinguish between liquid and vapor. Okay, it's on the border. Okay, so now we move to mixture. For mixture, let's say binary mixture, we have dew point curve below. Okay, below, and they are both. We have bubble point curve, right? And in between, we have Weber liquid region. Okay, the VLE, our VLE. So you see that, wow, the bubble point curve and dew point curve approach to the same connected at critical point also. Okay, so yeah, we have vapor here and liquid there, right? Is it connected to approach to the same point, right? And one thing is, of course, if we start from mixture over here, this point, and we are our mixture is vapor. Okay, the state is vapor. Okay, only one phase vapor, and then you pressurize it, increase the pressure. What happened? At certain point, it will condense. Okay, and form the first drop of liquid. At that point, we call dew point, right? And you further pressurize it, you enter the Weber liquid region. Okay, now our mixture contains two phases, Weber and liquid, right? Because we are at the Weber liquid region. And if we further pressurize it, what happened? Finally, we reach a bubble point curve, right? And over here, it's of course, it's still equilibrium, right? Mm-hmm. We call bubble point curve. And this is the last point where we still have a Weber, okay? or we can say that is the first bubble of, if we're moving down this way, is the first bubble, of course, but here's the last bubble of vapor. And then once we reach this point, it's totally condensed and form liquid, right? We move different way. We move from liquid down here. We move from liquid phase of mixture. Then we depressurize it. And once we reach here, it start bubble. Okay. For the first bubble, of course, we reach the bubble curve, bubble point curve. Down here, we in the zone of vapor liquid region. Okay. And finally, once we reach dew point curve, what happened? Most of the mixture vaporize, right? But of course, you still have small drop of liquid. Okay. I can say the last drop of liquid. Okay. You keep depressurize it, everything vaporize. Okay. Or you can move this way. Let's say we are at this point. Our mixture is liquid, and then increase the temperature, right? Once we increase the temperature, we reach here. What happened? Start bubble, and we enter the Weber liquid region. Okay, until we reach this point. Okay, the last drop, which is a dew point curve, right? Okay, and then everything vaporize. Okay, or we start from here and move this way. Of course, we reach the dew point first, and then bubble point curve. Okay, this is what I explained to you. These are normal case. Okay, but now consider this. What happened if our mixture is here at this point? At somewhere, the temperature above Tc. Tc is the critical temperature. Okay? And we pressurize it. What happened? We reach this point. Then hmm? Is it water? What happened once we reach this point? We reach the dew point, right? Dew point curve. And what happened? We enter the Weber liquid equilibrium, right? And then we increase the pressure and we reach this point. Why is this point? Hmm? Is the dew point curve. Once we pass the dew point curve, we reach this zone. Okay? Where we cannot distinguish between vapor and liquid anymore, this area. But what is the difference when we start from this point and we start from this point? When the temperature below Tc and above Tc, what happened? Can you say something? Can you explain it? Why is it different? Hmm? What's the different? when the temperature below the PC critical temperature, we pass dew point one time. We pass bubble point one time. Okay, we pass dew point once. We pass bubble point once. But once the temperature above TC, we pass dew point twice, right? We pass dew point curve twice. Okay. The same happen if we start from here. We start from mixture with pressure above critical point. Okay. But what happened this time? This time we pass bubble point twice, right? Once pressure is above PC and we increase the temperature, first it reach bubble point and then enter VLE, right? And then again, we pass the bubble point curve again. Okay. So there are two bubble points in this case. Okay. We have this point over here is called circumdent bar. Okay. And over here is circumdentum. Okay. Temperature and pressure, right? This is the last pressure we can enter to the vapor liquid equilibrium. With pressure higher than this point, the mixture cannot enter the vapor liquid equilibrium anymore, right? Over here, if the mixture is here at this temperature, it cannot enter vapor liquid equilibrium anymore. Okay, so what happened? What is the shape of the vapor liquid equilibrium mix when we consider different pressure and different temperature? Okay, we consider in case of high pressure and high temperature. It's at low temperature, of course. It's if we plot at certain temperature, we slide this right hand side figure. We slide this way. Yes, we keep the temperature constant, right? And then we slide it. It's from a two curve, right? Dew point curve or dew point surface at below. And above is a bubble point, right? Okay. But once you increase the temperature, you see that it's also change the vapor liquid equilibrium. Okay. And finally, all these curves, all this surface approach the same value at that critical point. Okay. Is well the shape like a sack. Okay. Okay. Also, if you cut this way, you consider constant pressure. You also obtain the same feature, right? And finally, you did sack. Well, it's a closed sack. Okay, where the surface of the bubble point and surface of dew point approach the same value over here at critical temperature. and pressure. Okay, this point. Okay, so the next thing is how can we calculate VLE at high temperature or high pressure? Sorry, at high pressure, because the behavior is totally different from at low pressure or even medium pressure. Okay, the easiest way to calculate it, can be done by empirical k-value correlation. Okay, this is empirical method. Okay, for example, here you need k-value correlation like this figure. Okay, you see that you can plot this one at certain pressure, right? Or at different pressure. Okay, you can read the pressure first and what component. Okay, you consider, and then you read for ki. Okay, and once you read ki, then you use that k for your calculation. Okay, but at high enough pressure, of course, k approach 1, right? At this pressure, k become 1. Okay, okay. The next thing is, well, you can use Charles-Seidel method by rewriting the ki as gamma I pi phi I hat t. Okay, you can look more detail in the book. Okay, chapter to calculate this one. Or you can use EOS, cubic EOS, to calculate the VLE directly. And of course, this requires computer programming to do that. Okay. Okay, but you need computer solution. Okay, so this is what happened at the high pressure. Okay. For detailed calculation of this, you can consult the textbook. Okay, so now we move to the next chapter where we deal with liquid equilibrium. Okay, also, well, liquid solid equilibrium and gas solid equilibrium. Okay, but mostly on liquid equilibrium. So what is the major application of LLE, liquid equilibrium? For VLE, you use it for distillation, right? And also flash calculation. What about LLE? And also liquid solid and gas solid equilibrium. The first one, liquid equilibrium. Why do we need it? Why do we need liquid equilibrium? Hmm? What is the application of liquid equilibrium?
Separation processes.
Pardon?
Separation processes.
Of course, you said separation. Even VLE also separation, right? Gas solid also separation, right? Everything separation, right? Can you be more specific?
Liquid extraction.
Liquid extraction. Yeah, is one thing. Okay. What about gas? Liquid solid.
Leaching.
Yeah, crystallization also, right? Also extraction. Okay, where you use liquid to extract something from solid. Mhm. Okay, there's an example. Okay, for liquid equilibrium, we start from liquid equilibrium first. We can separate, we can classify the system of liquid and liquid mixture into three possible cases. First, when both are totally miscible, what happened? If both liquids we mix, they're totally miscible. For example, we have water and ethanol. We mix water with ethanol. What happened? Hmm? Water and ethanol. We mix water and ethanol. What happened? They're totally miscible. So we don't have liquid equilibrium, right? It's nonsense to consider liquid equilibrium because we have only one phase of liquid, right? They both form a single phase. Okay. The second case, practically immersible. Okay. Forming two liquid phase, each of which contain only small amount. Okay. Small amount, it can be less than 1 mole percent. Okay. For example, water and most organic compounds. So in this case, the mixture contain two liquid phase, right? Two liquid phases. Okay. So we need liquid equilibrium in order to study its equilibrium, right? Because there are two liquid phases. Okay. And the third one, partly miscible. Okay. Of course, it's formed two separate phases, each of which contains substantial amounts, more than 1 mole percent. Okay. Like water and butanol. Okay. Alcohol. In this case, also, there are two phases, right? But it contains high amount of other component in the other component. Okay. So in this case, also, we need liquid equilibrium to analyze it. Okay. So in this table, it's solubility data for benzene. Okay, it's species 1 and water species 2. Okay. Well, we change the temperature. You see the solubility of 1 in 2. Okay. And also solubility of 2 in 1. All right. And you see how solubility change with temperature. Okay. This one is data of benzene and water. Okay. This case is immiscible case, right? You can calculate that it's less than 1 mole percent, right? So this is a very common way to report the data, okay, using table. And you see how solubility change, okay? And normally, once we increase the temperature, most of the time, the solubility increase, right, for both phases. Okay, this case we call practically insoluble, right? Because at 25%, it is 0.0405. Okay, that it's only 400 ppm, very small. Okay, so it is practically immiscible. Practically insoluble. Okay. What about other system like hydrocarbon in water and water in no, this is different. Not that one. It's practically insoluble. Okay, but we this table shows different components. Okay, water and pentane, water and hexane, water and heptane, and water and cyclohexane, benzene, toluene, methylene, methylene dichloride, chloroform, and carbon tetrachloride and monochlorobenzene. Okay, and you see the solubility in water. Okay, quite small. Okay, and this table report at 25 degrees Celsius. Now we move to the next one. Partially soluble liquid pairs. Okay, at 25 degrees Celsius. In this case, we can read some example like water and butanen. Okay, and you can compare solubility. Solubility is much higher than the previous case. Okay, cyclohexanol also. We have methyl ethyl ketone, methyl isobutene ketone, diethyl ether, diisopropyl ether, methyl acetate, ethyl acetate, and butyl acetate. Okay. What is the difference between the previous one and this group in terms of structure, molecular structure? Hmm? In terms of molecular structure, what's the difference between the chemicals report in this group and the chemical reports in the previous group? Hmm? What is it? What is it? Why is it? Why is it different? Can you raise some idea? Then you can guess if I read some example of a chemical, and then you can tell me whether this chemical with water it forms what's it insoluble, practical insoluble, or partly soluble system. Hmm? Yes, what is the difference? Tell me something. Pardon? The value. Of course, we know it's smaller because I told you at the beginning that solubility of this one is greater, much greater than the previous one, right? But in terms of molecular structure, what is the difference between these chemical and chemical in the previous table? Yes, they're both hydrocarbon. This one also hydrocarbon, right? This is organic, right? This one in the structure contains some functional group which induce polar structure, right? For example, butanol. Butanol contains hydroxyl, right? OH, okay? And it induces polar, right? Electronegativity is not balanced the charge. The what is it called? Electron density at every part of the molecule are different. Besides butanol, what else do we have? Cyclohexanol. Again, we have hydroxyl group, right? Methyl ethyl ketone, what do we have? The ketone group, right? Carbonyl. Okay. We have diethyl ether. Ether, again, you have oxygen inside the molecule. Ether group, right? Yes, ethyl acetate also. You have acetate group. Carboxylate. Butyl acetate also. Okay. And the other thing is, if the organic chain smaller, normally the solubility should be higher, right? Okay. If you keep increasing the length of the chain, the carbon chain, of course, solubility will be smaller and smaller, right? I mean, solubility in water. Okay. And now you can guess whether it's soluble or not, right? Okay. Okay. This is some example. You can read it. For example, the lower molecular weight alcohol, for example, methanol, ethanol, isopropanol, and the lowest molecular weight ketone are completely miscible, right? The next larger alcohol, like N-butanol, and the next larger ketone, like methyl ethyl ketone, are partly miscible. Okay, adding a second hydroxyl group to alcohol to make glycol increase the water solubility. Okay. Yes. Okay. Now we move to the next thing. We have what is ternary liquids, okay, mixture. We know that water and benzene. What happened to water and benzene? If we have binary mixture of water and benzene, water and benzene practically insoluble, all right, immiscible, okay, but water and ethanol is totally miscible, okay. What about benzene and ethanol? What do you think? Benzene and ethanol is totally miscible, okay. Now we consider ternary system. You can think of, well, we start from water and benzene, where it's practically insoluble, and then we add ethanol into the system. What happens if you add ethanol into the system? Of course, ethanol will separate. Part of it dissolve in water, part of it dissolve in benzene, right? Okay, you keep increasing ethanol. Once the amount of ethanol is large enough, it binds all the benzene and water into a single phase, right? It's formed a single phase containing everything, okay? So this is a equilibrium data where we have two phases, water-rich phase and benzene-rich phase, okay? And one line is one equilibrium, okay? But two phase, okay? For example, this line, yeah, it's the same equilibrium, okay? But different phase. So, how many equilibriums do we have? How many equilibrium? 12, right? We perform 12 experiments, okay? Each are identical, no, not identical. Each are different equilibrium, okay? We can plot this data in this form. In this form. This form. Okay? One on the left hand side. Yeah. As I told you that we have one equilibrium, we have 2 points, right? Different phase. On the left hand side and on the right hand side. Okay? They are the same equilibrium point. Okay? And if we draw a line between the point on the left hand side and on the right hand side, okay, we call it the tight line. Okay, tight line means, well, it's a line that hides between 2 points in the same equilibrium. Okay, and we can construct this curve. Okay, and what does it mean for this curve? In this curve is a region of 2 phases. Okay, we have liquid equilibrium in that region only. Okay, beyond this point, one moment. Okay, beyond this point, I mean this area. This area is one phase region. What does it mean, one phase region? One phase region means, well, there are no liquid equilibrium. The mixture contains only one phase, right? That's why we call it one phase. Okay, one phase region. Okay, everything totally miscible, right? You can, as I mentioned to you, that we keep increasing the ethanol, right? Over here at this corner is pure ethanol, right? That means, well, in this region, the mixture contains high amount of ethanol, right? That means, well, you have high amount of ethanol, and ethanol can dissolve benzene, also dissolve water, okay? So it can, what is it, handle all benzene and water into single phase, right? Okay? So this region is one phase region, okay? You only have liquid equilibrium when the liquid, when the mixture contain, your mixture contain ethanol lower than this point, okay? This region, okay? Anything, the mixture contain the composition under this curve will separate into one phase and the first phase and the second phase, okay? At the same, what is it, equilibrium, okay? And if you identify that your mixture, for example, your mixture is here in this tight line, for example, this tight line, you can see my cursor, right? Okay. If your mixture contain, for example, if you mix ABC, okay, in this case, water, ethanol, benzene, with composition, this point, it will separate to one phase with this composition and this composition. Okay? Okay? It separate to this composition and this composition for sure. Okay? And if you want to know the amount of each phase, you can use Lever rule, similar to what you use in VLE, vapor liquid equilibrium, right? I mentioned to you, well, a few weeks ago, right, about Lever rule. For example, if it is this line, for example, this line, okay, this line, at this point, you want to know the amount of this phase. You take this length, okay, divide by the overall length, okay? You know the fraction of that phase, okay? Okay, let us stop for 5 minutes. I feel like short throat.
Excuse me, Professor. We are not able to hear your voice.
Hello? Sorry, can you say again?
Oh, okay. We could not hear your voice before, but
Yeah,
now.
we break. We break for 5 minutes. You don't hear
Oh,
me?
okay, okay.
Okay. Okay. So any questions? Any questions? No? All right. So now we see the region for two phase, right? And a region for one phase. Let me check. Okay. So if you look at in the textbook, in the file I sent you, see that on the right hand side, that one should be ethanol. Okay. I corrected here in this line. Okay. Small fraction of ethanol in that on the right hand side. Actually, this data contain redundant information. Okay, redundant information. We don't need three axes like triangular shape like this. We can plot using only two. Okay, two axes. Okay, and if we plot one thing first, let me explain this thing first. Okay, before we go to that information. First, we have two regions. One is for single phase, and the second one is for two phase. The question is, what happens if temperature change? Okay, if we increase or decrease the temperature, what is it going to happen to the shape of this curve? Okay, so it can be, of course, it depends on the system. It can be changed. It can form something like this, or this in the middle, and on the right hand side. Okay, what is the difference between these three things? First, you see that we have two separated region for single phase. Okay, because the area in that area, it's area of liquid equilibrium, right? And if temperature change, for example, this case, it can be change the shape of the two phase region can be changed, of course, can change, and it's only touch that. But anyway, in the middle is also form two regions, okay, for single phase. And in the rightmost, this one, the region for single phase, there's only one region, okay, for the single phase. Okay, so you change it in some system, you change the temperature, and most of the time, you change the temperature, you change the shape and area of the two phase and one phase region. Okay, then of course, because you change the temperature, the solubility of each component change, right? Mm-hmm. What about this one? This one is what is the component of this one? Water and in butanol? No? No. What is it? I don't know. What is the other component? Mm-hmm. Water with something. Okay. Well, if we for this one, it from one region, one phase region, a single phase region, and two phase region. Okay. And if we change the temperature, of course, you see the interval that we can form two phase also change, right? For example, you can look at the horizontal line at 40, for example, 40 degrees Celsius. You see, at 40 degrees Celsius, we can form two phase from this concentration to this concentration, okay, approximately. And if you increase the temperature to 100, okay, you can only form two phase region with this concentration to this concentration, right? However, if you keep increasing the temperature, this is where you can form two phase region. Okay, the last temperature that you can form two phase region, right? Beyond above the temperature above that point, you cannot form two phase region anymore, right? Okay. In this case, we call that temperature as upper critical solution temperature, bro. Okay. Or UCST, upper critical solution temperature. And you see that we can induce the composition in each phase by just changing the temperature, right? We have information regarding the liquid-liquid equilibrium. And if you want to induce a new phase with different concentration, of course, you just manipulate the temperature, okay? And this one, figure 4, is different, opposite way. See that if we increase the temperature, the two-phase region is larger and larger, right? And if we cool it down, right? The two-phase region smaller and smaller, okay? And we can have the two-phase region at the lowest temperature here. Okay? We call it LCST, that temperature. Lower critical solution temperature. Okay? For some system, we have both LCST and UCST. Okay? For example, that on the right hand side, this one, we have both LCST and UCST. Okay. Okay, now we want to model the liquid-liquid equilibrium. Remember that for PLE, we model it by setting the Fugacity of each component in each phase becomes identical, right? Equal. Okay. The same for liquid-liquid equilibrium. Okay. We have two phases. They are both liquid. Okay. But different phase. Liquid 1 and liquid 2. Okay. We identify the equilibrium. Okay. By setting Fugacity of phase 1 equal Fugacity of component I in phase 2. Okay. And again, they are liquid, right? Well, you remember previously we deal with VLE, Fugacity of liquid phase. How can we calculate the Fugacity of the liquid phase? We estimated using what? Fugacity of liquid phase equal Fugacity of set liquid, right? And we can estimate the Fugacity of set liquid by Fugacity of set vapor pressure. of that component, okay, at the same temperature. So, so we can write xi gamma pi, right? Okay, it should be pi, the same component, xi gamma pi at certain phase. Okay, at phase 1 and at phase 2. But if we, what about pi? Pi, side pressure. Yes, a pure component, right? So for both sides, it should be identical. So what you have now is xi gamma of phase 1 equal xi gamma of phase 2. Just that. Okay? So it is mole fraction of component I in phase 1 times with activity coefficient of component I in phase 1. Okay? Equal xi mole fraction of phase I in component 2. No, in phase 2, right? Times with activity coefficient of component I in phase 2, right? Okay, so or xi equal xi in phase 1 equal xi in phase 2 gamma I in phase 2 over gamma I in phase 1, right? Yes. Now consider the case where the mixture is practically insoluble, immiscible. Okay, when we consider the case where the mixture is practically immiscible. For example, benzene and water. If you look at the liquid containing rich benzene, the concentration or the mole fraction of benzene approach 1. Okay, because most of component there, it's benzene, right? And what is the Fugazzi coefficient? No, not Fugazzi, nothing to do with Fugazzi. Activity coefficient of benzene in that phase. In benzene rich phase, gamma is 1. Gamma is 1, right? Because it's close to pure component, right? Okay, when X approach 1, of course, gamma approach 1 too. Okay, so you see, the mole fraction of benzene in water rich phase times with activity coefficient of benzene in water rich phase must be equal 1, right? Okay, or you can write mole fraction of benzene in water rich phase equal 1 over activity coefficient of benzene in water rich phase, right? Is analogous to water in, yeah, a water component, right? This is for practical insoluble species, okay, in binary mixture. And again, if we start from G mixture is G solution, all right? Gives energy of solution of the same composition. But ideal, right? It's ideal. Plus excess property. Okay, excess skip property. Then we can write G mixture is summation of xi gi0, okay, which is ideal, right? Plus summation of xi rt log natural log, of course, xi plus summation of xi rt log gamma, okay? Okay, so if we know the activity coefficient model, we can replace this log gamma I by our activity coefficient model, right? It depends on which model you have. But this one we replace with this model, okay? Log gamma is a times with 1 minus xi squared. Okay. Now G mixture it's the same. Okay. So we just replace here. We just replace the activity coefficient here. Okay. We can plot the change of Gibbs energy with mole fraction of species. And you see that the shape of this Gibbs energy depends on the activity coefficient model. Okay. For example, if we use this model, okay, and we change this A parameter, this parameter, we only have a parameter here. You see that if A equals 0, what is it? A equals 0, so log gamma becomes 0, right? What does it mean? Log gamma becomes 0. Gamma is, pardon? If log gamma is 0, what happened to gamma? Hmm? Hmm? Pardon? I have a solution, yes, but my question is, what is gamma? Gamma is if log gamma is 0, then gamma is 1. Yes. Ideal solution, right? But gamma is 1, right? Okay. So in that case, if it is ideal solution, then gamma is 1, right? So if the G follow this line. Okay. So what does it mean? We will never have liquid equilibrium. Okay. The liquid will never separate. Okay. So it's impossible to form liquid equilibrium. Okay. And what happens if A is 1? Still, even A is 1, we have only one stable phase. We never have two phase. Okay. A is 2 also, but once A is larger than 2, A equals 3, we can have two stable phase. That means we can form liquid equilibrium. Okay. You know, it's why we have that two stable phase, because we can draw a line with where the line touch the curve 2 times. Okay. If we can draw only one slope at each point, then it's only one phase. Okay. But once A equals 3, of course, we can draw the line touching this point and this point. That means, well, we can form the liquid equilibrium. Okay. Okay. So it depends on activity model. Okay. If our mixture is component, we have differently. Okay. We can study it using from activity coefficient model. If we know exactly the activity coefficient model for each component, we can study we can check whether our mixture can separate into two phase or not. Two phase mean liquid. Yes. Okay. Now we study the effect of temperature on liquid equilibrium. Okay, we start from, I think you are familiar with this equation already. Yeah. The change of log gamma depends on, well, respect to temperature change, depends on, what is this? What is it? Mixing. Heat of mixing, right? Mhm. If you want to find how gamma change respect to temperature change, you need information of heat of mixing. Okay. And you integrate this expression. Okay. Normally we have to write this heat of mixing as a function of temperature, and then you integrate it. Okay. With temperature. Or if you assume that HI heat of mixing is constant, we can write log xi. We can integrate this directly because this is constant, right? We assume that. And log xi equal HI0, the heat of mixing, over RT plus constant, right? By integrating this. So if you have information of xi and t, you can estimate this value, right? All you have to do is you plot between log xi and 1 over t inverse, right? So the slope of this one is heat of mixing over R. Okay, this is one way to measure the heat of mixing. Okay, so normally you see the curve, yeah, the experiment, yeah, graph like this. Okay, even plot between log xi and 1 over t. Okay, it is thousand of 1 over t. Okay, and we take the slope. Okay, and the slope is heat of mixing over R. Okay, the next one is distribution coefficient. For distribution coefficient, we define distribution coefficient as, imagine that we study ternary system. We have benzene phase and we have water rich phase. Okay, and we have ethanol to the system. Now it's ternary system. Then we measure the mole fraction of ethanol in water rich phase and mole fraction of ethanol in benzene rich phase. Okay, this ratio we call it distribution coefficient. Okay, and of course you can write as gamma of ethanol in benzene rich phase and over gamma of ethanol in water rich phase. Yeah, it's the same. Okay, Any questions? Sorry, one moment. What happened to computer now? Sorry. Okay, so what does this mean if k is greater than 1 and k less than 1? If k is greater than 1, it represents what? It represents what? When k is greater than 1, what does it mean? Hmm? Hmm? If k is greater than 1, what does it mean? Huh? Pardon?
What expression? Maybe
Yeah, you see that in this case, it's what is it? K. What does it mean? The mole fraction of ethanol in benzene rich phase, right? Over mole fraction of ethanol in benzene. No. Sorry. Mole fraction of ethanol in water rich phase over mole fraction of ethanol in benzene rich phase. If it is greater than 1, moles of ethanol added to the system will, well, stay in the water rich phase more than benzene rich phase. This is correct. And it's applying to other system also. If you have K greater than 1, what does it mean? The component you are interested in tend to stay in one phase more than the other phase, right? So you can use it to, if you want to extract something. Okay, let's say you have binary system of A and B, and you know that you want to extract A from mixture of A and B. You need other phase, right? With, when you consider k must be greater than 1. Okay, what does it mean? The mole fraction of A in your new phase, right, must be greater than the mole fraction of A in the mixture. Okay, then you can extract one component from binary, right? It is useful for design the liquid extraction, right? Or in this case, when k is greater than 1, if we have ethanol dissolved, a mixture of ethanol and benzene, you can use water to extract ethanol from that mixture, right? If k is greater than 1. Okay, now we move to liquid solid equilibrium. Yeah. For liquid solid equilibrium, for example, we consider solubility, of course. Yeah, we can start from a very simple one where equilibrium of sodium chloride in water. Okay, But this one is solubility, the information of the solubility of salt in water. Salt is a sodium chloride salt, sea salt. And what does it mean? What is solubility? What is the meaning of solubility of sodium chloride in water? It shows, this table shows how much sodium chloride can dissolve in water at certain temperature, right? For example, at 0 degrees Celsius, the solubility of sodium chloride is 35 plus 7. Okay? The unit is gram per 100 gram of water. Okay? So, this is gram per 100 gram of water. Okay? So, what does it mean? In 100 gram of water, it can accommodate 35.7 gram of sodium chloride. Okay? If you, for 100 gram of water, if you add sodium chloride less than 35.7 gram, you will never have liquid solid equilibrium. Yes or no? Yes, right? Even at 35.7 gram of sodium chloride, you never have liquid solid equilibrium because all the solid, I mean your sodium chloride, can dissolve in the mixture in water, right? If you want liquid solid equilibrium, you must add more sodium chloride to the system. Okay, so if the temperature increase, the solubility limit, solubility of sodium chloride increase also. Okay, and at 100 degrees Celsius, the solubility of sodium chloride reach 39.8 gram. Okay, so you see that it increase with temperature, right? Solubility increase with temperature. My question is it always true? For any component, always true like this? Yes or no? Increase temperature, then solubility increase? Yes? Really? It depends. No. Not all salt have the same behavior. Okay? The very common one is calcium salt. For calcium salt, you see that we increase the temperature and solubility decrease. Okay? What does it mean? If you want higher solubility, you must cool down the mixture. Okay? No strange, because well, you have spring well in your country? No? Or even you have what is it? Hot water pipe. Yeah. Is it really easy to form the scale? Why? Because solubility of calcium is lower, right, in high temperature. So it at high temperature, if you work with high temperature, the sodium ion tend to precipitate, right? Because it cannot dissolve, it must precipitate in some form. Okay? So this is the reason why in the cold country, there are two pipes, right? For cold water and hot water. If you want to drink water from directly from tap water, it's okay. But drink from the cold one, not the hot one, because for the hot pipe, there's so many scale inside. Yeah, we don't know. Okay. And also, when you work with boiler, it's very easy that the scale can form, right? Very easy. So you should take care of what is it? The iron, especially that calcium salt. Okay. Okay, we can present the data of liquid solid equilibrium as this phase diagram. This one is interesting. This one is a phase equilibrium of sodium chloride in water, okay, with different temperature. What do we have now? We have a region for unsaturated brine, okay? You know unsaturated brine, right? It's brine, okay? This one, unsaturated brine. Of course, for unsaturated brine, you have concentration. It depends, okay? Because it's not saturated yet. It's unsaturated brine. Okay? So, over here on this axis is pure water. Okay? No surprise because sodium chloride is 0, then it's pure water. And the freezing point is 0. All right? It's 0. Okay? So, the brine of course contains salt water, contains some sodium chloride. Okay? For brine, the freezing point become depressed, right? Smaller, lower than 0, right? Sub-zero. Okay? But here it's an equilibrium, right? Equilibrium of X. Anything, any point in this zone is a equilibrium between ice and brine. Okay? What does it mean? The mixture inside this will separate into your battery is running low. Oh, sorry. Not my battery. This one. Oh. Yes. Okay. For this zone is a mixture or equilibrium between brine and ice. It is area of liquid solid equilibrium. What is liquid in this case? Brine, right? And ice. Okay. So it will separate to brine and ice. Okay. For example, if you start from brine at this concentration and you cool down to here, of course, it's at equilibrium, right? It will be saturated brine, right? But once you keep decreasing the temperature down to 10, let's say 10, okay? It separates into ice and brine, okay? What is the concentration of ice? The concentration of ice is 0 sodium chloride, okay? And what about brine? The concentration of brine, you should look at this 10 degrees Celsius. Yeah, Okay. The concentration, of course, increase because you lost some water. Because some water already formed ice, right? Okay. And over here, it's a eutectic point. Okay. This is the last point we can have unsaturated brine. Okay. Beyond this point, of course, everything turns to eutectic. Okay. Pardon?
Why? And why?
Why?
Yeah, because too solid.
No, it's eutectic. Of course, it's a solid.
Oh, solid.
Yes. One type of solid. Okay. We call it eutectic. Yeah. Of course, what you mentioned is in case of what's it alloy. Of course, we have eutectic also. Yeah, but this one also eutectic. Fine. Okay, so well, for example, if we start from here, right, it's reached the equilibrium of the saturated brine, right? Here it's separate to ice and brine, right? When it's reach this area, it changed to ice and eutectic. Okay, what does it mean? Eutectic. Eutectic is solid of that brine. Okay. Yeah. These are also eutectic, right? More system involving water and solid in which the liquid has negligible solubility in the solid phase. It's not case. Okay. Okay. Now we consider what is this? Tin and I think lead. Lead. Lead and tin. Lead boom, PB. Okay. So this is the alloy system. Okay. We need a high temperature, of course, to make it alloy. Okay. Liquid phase for both. Yeah, liquid phase of mixture. And we have eutectic here at 61.9%. Okay, this is our eutectic. And you see that this is the freezing point of lead. And this is the freezing point of tin. Right? 100% tin. Yeah, this is the freezing point of or melting point. You can call melting point. Okay. And you see that we can alloy of tin and lead. The melting point can be lower than pure component, right? Because for lead, pure lead, the melting point is here. Pure tin, the melting point is here. Okay, when you mix it, you can form liquid phase, even lower than this point and this point. Okay, and the lowest one is eutectic point here. Okay. And this one, we solder. Yeah, used for electronic. We use alloy. We don't use pure component. We are pure metal. Why? To make a solder. Why do we need alloy? And most of the time we use eutectic composition. Why? You know solder why, right? Primitive way. You use solder why and you heat it okay, to make it melt. So if you use pure metal, you need very high temperature. Okay, but if you work with eutectic, you don't need such high temperature, right? You heat it until it reach that melting point, and you can melt it. Okay. Yes, eutectic. Okay, the rest please read the rest of this chapter by yourself. Okay. For gas solid equilibrium also, yes, please. And then next time we move to the next chapter regarding the chemical equilibrium. Okay, where we have reaction. Okay, simple reaction and then complex reaction. Okay, we will meet again next week, next Friday. Okay. Not this Friday. Next Friday. Pardon? No, not public holiday. I'm not here. I will be away. This Friday is Loi Krathong. Loi Krathong is not public holiday. You just enjoy it during evening. What? You pay respect to water, god of river. Yeah. Okay. So we finished today.